In this video, we turn our attention to an important property of amines, and that is that amines are basic. When we think about pH of a solution of water, if we mix an amine in water, typically the pH of that solution is going to fall greater than 7. Remember that 7 is neutral pH. Instead, it's generally going to be up here somewhere in the 10 to 11 region, right here with ammonia, because remember ammonia refers to NH3, which of the things on this various wheel of pH scales, this is the closest relative of the amine molecules that we are talking about here, and hence the pH of an amine is similar in roughly the same ballpark as ammonia. So let's first take a closer look and a bit of a reminder about what are we referring to when we talk about a base. I'm going to give you two different descriptions or definitions of ways to look at a base. The first is if we take a base, which I will abbreviate generically here as B, with a lone pair of electrons, because in order for a substance to act as a base, it typically needs a lone pair of electrons. If you mix it with water, water is a switch hitter. Water can act as an acid or a base. That's one reason why water is essential to life. What will happen when you mix water with a base, such as ammonia, is that the lone pair electrons from ammonia or an amine or whatever base we're dealing with will come over. They will grab a proton or steal a proton from water, which acts as the acid, the proton donor. That will force the bond between hydrogen and oxygen to break, and the electrons of that covalent bond have to go somewhere. They go into the more electronegative of the two atoms, that's the oxygen atom, to form, as a result of this acid-base reaction, they form the so-called conjugate acid over here, which is the product that results from our base, which we abbreviate as B, picking up a proton. So BH is our conjugate acid. Our conjugate base, on the other hand, is what happens once our acid, in this case water, has lost a proton. Once it loses a proton, it becomes from H2O to OH, making it the conjugate base. So what we're showing here by these electron pushing arrows is that the base will use its lone pair of electrons to grab a proton from the acid. So in other words, the acid, a term that we will use to describe this, is that the acid is the proton donor, where the proton is H+. So the acid, in other words, is losing a proton, and it's giving it to the base, where the base we could then describe as the proton or H+ acceptor. As a result of B, which we show here is neutral, it has no formal charge on it, accepting H+, a proton, that's why BH, our conjugate acid product here, has a positive formal charge on it. And on the flip side, our acid, our proton donor, once it has lost that H+, it becomes OH-, so that cancels, the charge cancels out there. So I will be using throughout this video the terminology of base and acid for what's on the left side of the equation, and then conjugate acid and conjugate base for what's on the right side of the equation. What will always be the case is that the base on the left, once it picks up a proton, will become the conjugate acid. The acid on the left, once it loses a proton, will become the conjugate base. Another way to explore what is a base is rather than having the base react with water, we could instead have the base react with hydrochloric acid or some other relatively strong acid here. And we'll use HCl because later on in this video, we're going to see how this has important implications in drug design and drug formulation, to be more specific. So looking at our base here, we have this lone pair of electrons again, and what happens, analogously to the reaction with water, where water was the acid up top, HCl is going to be the acid down here. So the base comes over, it grabs a proton, H+, from the acid, hydrochloric acid in this case, that forces the bond between H and Cl to break, and the electrons go on the more electronegative atom, once again, much like they did up here, going on to the oxygen. Now, once this has happened, we follow through what went on with our electron pushing arrows, where we showed the lone pair electrons here from the base coming over. They're forming a covalent bond to the proton. That gives our conjugate acid BH+, because the B, which was neutral, is picked up H+, so it becomes BH+. as a consequence of that. We break the bond between H and Cl. The electrons from that covalent bond go onto the chlorine, so chlorine has now picked up an extra lone pair of electrons. That confers a negative formal charge on the chlorine. In this case, the chlorine is the conjugate base, because remember the conjugate base is what results from the acid losing a proton, whereas conjugate acid is what results from the base on the left, that was B, picking up a proton. So let's apply this information toward amines specifically. So here I have redrawn the reactions that we saw just a moment ago of B representing our base reacting with our acid being water or HCl to give the conjugate acid and conjugate base products. We can fill in these generic placeholders rather than using B with an amine. Let's take a look. I'll fill in my generic amine as N with 3 R groups bonded. These 3 R groups could be identical to one another, or they could be 3 different R groups. They could be 3 alkyl chains, 2 alkyl chains, and a hydrogen, 2 hydrogens, and 1 alkyl chain. Whatever you like to put in there, the reaction is going to take place through the same pattern regardless. Remember that the nitrogen has a lone pair of electrons on that nitrogen atom in the amine. That is essential for the property of this to be able to act as a base. When it is mixed with water, like so, it forms an equilibrium reaction. The reaction is an equilibrium because nitrogen is a relatively weak base, meaning that at equilibrium, part of the material in the container would be the amine and water. The other part in the container would be the conjugate acid and conjugate base. And let's show how those form. Those are going to form following the template that we had down here of the base uses its lone pair electrons. In this case, amines are basic, so we have the nitrogen atom here that's available to use its lone pair of electrons to come over, form a covalent bond through that electron pushing arrow to a proton donated from water, our acid, that forces the oxygen-hydrogen bond to break and the electrons to go onto the oxygen. So drawing this out here, we have our nitrogen with our 3 R groups, that is either hydrogens and or alkyl groups. And now in blue, I'm going to show our new bond that we have created to a hydrogen atom. That hydrogen was specifically a hydrogen donated from water, which was acting as our acid. So I've shown the hydrogen here, red highlighted here. That's the proton that comes over to here. Or a proton is just our name for a positively charged hydrogen. So in other words, the hydrogen that breaks away from here. That is going to cause the nitrogen to have a positive formal charge now. If we were to calculate the formal charge rigorously on a nitrogen, we would find that nitrogen with 4 covalent bonds and no lone pairs would have a +1 formal charge. And we can also intuitively determine that there has to be a +1 charge there because the nitrogen lone pair came over and picked up a positively charged proton. So that gives a net charge of +1 over here on this molecule. The other product of this reaction, that is the conjugate base, would be the hydroxide anion. And this is why when we mix an amine with water, the pH of the solution is going to be greater than 7, in other words, in the basic range, because of this hydroxide anion product, because pH measures the concentration of hydroxide anions in an aqueous solution. So keeping this reaction mechanism, that's our electron pushing arrows here to illustrate for us what's happening, we can similarly use this scheme down here to show what happens when we mix an amine with HCl. So we have our amine. Again, the 3 R groups there could be hydrogens and or alkyl groups. I mix the basic amine with HCl, our acid. I'm going to show this as an equilibrium reaction again. And like we saw up top, reacting with water as our acid, down here HCl is our acid, so the nitrogen comes over, using its lone pair of electrons to form a covalent bond to the proton here, donated from our HCl acid, that forces the bond between H and Cl to break, so that the hydrogen there doesn't exceed its maximum allowable number of covalent bonds of 1 covalent bond. So this HCl has to break in order for this nitrogen-hydrogen bond to form. When that breaks away, that's going to give us chloride, and the chloride is going to have an extra set of lone pair electrons relative to the start. In other words, rather than having 3 sets of lone pair electrons, it will have a 4th set donated from the covalent bond that broke between H and Cl right here. So that gives us chlorine with 4 pairs of electrons, 4 sets of lone pairs in other words, and the chlorine then is going to have a negative formal charge. On the other hand, our nitrogen will still have its 3 R groups bonded to it. Those nitrogen carbon bonds are relatively hard to disrupt, and so those stay in place. And a hydrogen atom or proton is going to have been donated from HCl. We saw that here when the nitrogen came over and picked up the proton to give us this as our product. And we'll go ahead and put our positive formal charge, don't forget that, on our nitrogen atom because again the nitrogen has picked up a proton from the acid, hence our net charge over here is going to be +1. So let's apply, now that we have looked at this in general terms, this information toward a few specific example problems. Here we are asked to predict the products of the following acid-base reaction. This is where we get to apply the info that we've looked at over the last several minutes towards some actual problems. So we take our amine here, reacted with HCl. Even though in our line angle formula we don't explicitly show the lone pair electrons there, if nitrogen has 3 covalent bonds, which it does in this case, and no formal charge, that implies for us that there has to be a lone pair that is hiding there. So what we can do, if we're showing how the product forms through this so-called reaction mechanism, we take the nitrogen lone pair electrons. Those are going to be drawn toward the positively polarized proton there. When the nitrogen forms a covalent bond to the proton, that forces the bond between H and Cl to break, and the electrons from that to go on to the chlorine, which, much like with the amine, we didn't show the lone pair electrons on the chlorine atom there because it was a line angle formula that we were working with. So now we have NH3, because we started here in this primary amine with NH2. It picked up an extra proton, so it becomes NH3. That is going to put a positive formal charge on the nitrogen atom. And we also have our chlorine to deal with, which is technically a chloride anion, because the chlorine originally had 3 sets of lone pair electrons, and it picks up a 4th when this HCl bond breaks. So with 4 sets of lone pair electrons, that gives it a negative formal charge. And these two, the cation and anion, would form a complex because of the fact that they have opposing formal charges. And so it would be impossible to separate these two from one another because of the fact that they have those opposing charges and they're needed in the solution to counter one another. Now let's take a look at this other example problem here, where in the starting structure, we would have our amine, which has 3 covalent bonds, 1 to a hydrogen and 2 to the alkyl groups. This is a secondary amine, in other words, reacted with water. What would happen here is that, again, there's a lone pair of electrons in the nitrogen there because it has 3 covalent bonds, and if it's 3 covalent bonds and no formal charge, it means there has to be a lone pair there. And we have it reacting with H2O. I'm going to draw H2O out a bit more explicitly for us here so that I can show what's happening in the reaction mechanism. So we have our H2O, like so. The lone pair electrons from the nitrogen will come over, grab a proton, stealing it from the water, which is acting as the acid here. That forces the HO bond to break and the electrons to go on to the oxygen. And now we can draw out our conjugate acid and conjugate base product. Our conjugate acid will represent the amine that has picked up an extra proton. So it's no longer an NH group here, which is what we had to start with, but instead it's NH2. And then we still have this carbon-containing group down here, which I will draw out. And we would have a positive charge on this nitrogen now, since the nitrogen has 4 covalent bonds and no lone pairs. We've also broken away the hydroxy group here, the OH group in other words, And so that would become OH minus, because I had two sets of lone pairs to start with, picks up a third by breaking that covalent bond. That gives a negative formal charge because now the oxygen has one covalent bond and three sets of lone pair electrons here. And we could label this, if we were asked to identify the conjugate acid, we would call the conjugate acid this structure here, as well as the one down here. The reason why we call those the conjugate acid is the conjugate acid what results when we bring a proton into a base. So we had our base, we brought in an extra proton, it becomes the conjugate acid. On the other hand, the conjugate base is what results when we take an acid and it loses a proton. So in other words, when HCl loses that proton and becomes Cl minus, it becomes the so-called conjugate base, Cb for short. Now, to wrap up this information about amines acting as bases, let's take a look at a real-world application of this. Very, very commonly, pharmaceuticals are produced as so-called HCl salts. And HCl salts, you can recognize if you look at the label for medicine, and this is true of a variety of anti-allergy medicines, antibiotics, and a plethora of others, you will see the name of the drug, such as this drug, sertraline, which is also known as Zoloft. Sertraline is the generic form of this anti-anxiety medicine. And you'll see it listed here as sertraline HCl. And what does that mean? You'll very commonly see HCl listed behind the name of a medicine. And I would not be at all surprised if you look through your medicine cabinet, you will very, very likely find something in there that has the name of the drug tagged with the term HCl. What that means is that the molecule itself, in this case Zoloft, or sertraline, as the generic name for that molecule or that drug, has this structure. And this is just sertraline as is. When we say sertraline HCl, which is the common way that this is packaged as a drug, that means that in a 1-to-1 molar ratio, the sertraline molecule was mixed with HCl. What happens when sertraline is mixed with HCl is that predominantly when we mix with this relatively strong acid, the reactions that we have just been looking at will occur, and the nitrogen atom, that's the only amine group in this entire molecule, it's the only basic group in the entire molecule. The nitrogen lone pair electrons come over and grab the proton like they did for our more simplistic examples. That forces the HCl bond to break like so, and the product of that will then have our nitrogen now having two hydrogen atoms. It will still have that methyl group bonded, and it will still have the ring structure here, the aromatic ring next door to that, and then the other ring down here that I'm just going to abbreviate with a squiggly line there because I'm approximately running out of space. And that will place a positive formal charge on the nitrogen now because the nitrogen has picked up that proton. We will also generate, as a result of this reaction, chloride anion. And the chloride anion and the nitrogen cation will be inseparable because of their equal and opposite charges. Now, why in the world would, in the drug optimization and drug formulation process, why would we react HCl with our amine molecule here? Well, the reason is because charged substances will have greater water solubility than ones that do not have that charge. And so in thinking about formulating this molecule so that it can be taken orally and readily, by reacting with the acid, that creates this molecule which is much more water soluble than the starting material. And so by increasing water solubility, this becomes a more readily accessible drug.